Okay, good day. This is AP Calculus. I am Mr. McCully, and this is the presentation for section 1.2, finding limits graphically, numerically, and analytically. All right, so let's get right to it. And today we are going to estimate the limit using a numerical or graphical approach. We're going to learn the ways that a limit can fail to exist, and we are going to study and use the formal definition of a limit. So, what is a limit? The book definition says this: the limit of a function at a given value c, so c is a constant somewhere on the x-axis, is L. L is a constant on the y-axis. The value that the function approaches as the independent variable gets arbitrarily close to the given constant c. So basically what it's saying is that as the independent variable, the x value, gets as closer to c, the limit of the function gets closer and closer to L. And so we have some notation for this limit, and the notation is this. So here's my notation. Here is how you read that notation inside these parentheses. The limit of the function f of x as x approaches c is L. So the limit of the function f of x as x goes to c is this limit L. Okay. So the existence of a limit, what it takes to exist. Now I have right here, and I'm going to put a link to this in the description. So what I would like you to do here is take a minute and pause, and then follow this link right here. It's a nice little animation. It does a very good job, better than what I could do in drawing in this particular setup. And so take a couple seconds. It's not real long. Take you about another 5 minutes. Pause the video and go watch this. So pausing, 3, 2, 1, moving on. I hope you enjoyed that video. So basically, for a limit to exist, so for a limit of a function at some value c to exist, three things must occur. Both the left and the right-sided limits must exist. The left and the right-sided limits must be the same. Now here is the kicker. The function does not need to be continuous at that particular value c. And that is the most important part of this whole limit definition. Because if the function had to be continuous at c, calculus would basically fail to work in a number of different aspects. Derivatives and integrals will not work. So you saw in the video about the burnt down, there was a little burnt down cottage or burnt down restaurant. That's essentially what this is saying. Where both the left side and the right side have to arrive at the same place, even if that place doesn't exist. All right. So we can move on to delta-epsilon proof. Now this is the formal way that we prove the existence of a limit. Now this proof tends to be very challenging for students because it usually ends up early. It's hard to understand, it's hard to define, but I'm going to make this promise to you. I am not going to do any of the real hard delta-epsilon proofs. I'm not going to ask you to do a hard delta-epsilon proof. But I definitely want to introduce this because it does try to define some kind of hard concepts. It's not necessarily on the AP Calculus exam, but it's definitely going to be on any college level course that you would have. So at least we'll get an introduction to it. And so basically what happens, this is as mathematicians in high school, we like things that are defined. We like answers that are, x equals 2. We're getting close to the end. How close? 0.1 to the end or something like that. This term arbitrarily, how close is arbitrarily close? Well, arbitrarily close literally means any value. And so we have to come up with a way to formally show what this arbitrarily close means, and that's this delta epsilon proof. And so basically it's set up like this. We're going to say that there is some epsilon that's greater than 0, and we're going to take the function and we're going to subtract the limit value, and we're going to take the absolute value of that. And we're going to say anytime that we have the function minus the limit that's going to be less than epsilon, we're going to have the independent variable minus that constant value on the x-axis that we're trying to find the limit for. It's going to be less than some delta. And what we want to do is we want to relate the epsilon and the delta together. And so what we're trying to say, for any epsilon that you pick, regardless, it's arbitrary, whatever epsilon you pick, I can relate a delta that's related to this epsilon so that that distance, so that c will always be inside that distance. Now, that's kind of challenging, but when you see it graphically, it makes a lot more sense. And so here we have a limit. Yeah, so we're saying the limit as x approaches c for some function x is equal to L. So what we're saying is here we have our function L, and I'm picking this constant here. So as x gets closer to c, and again, this is my x-axis right here. Here's my y-axis. And so as I get closer to c from both this side and this side, the function gets closer to that L from that side and that side. All right, let's go back and erase that because I don't want to put that in there for my drawing. But what I'm saying is I'm going to pick some absolute value epsilon, some distance epsilon, and it doesn't matter. It's arbitrary how far I'm going to pick it. So there's epsilon, both sides. If I pick some epsilon, that there must be some distance away from C that I can measure both to the left and to the right that is delta away. And so as epsilon changes, either gets bigger and smaller, delta changes. And what we need to do in the delta epsilon proof is try and find the relationship between epsilon and delta. Okay, so how are we going to do that? Well, so we're trying to prove this limit. This is our process here. We're going to try to prove this limit here. And so we're going to set up two statements. First thing we're going to do is we're going to say let epsilon be greater than 0. And we're going to set up this statement. We're going to say f of x minus L. So we're going to take the function and we're going to subtract whatever limit we're going to try to find. We're going to say it's less than epsilon. And then we're going to take this x and we're going to subtract this constant c. And we're going to say that's less than delta. And then what we're going to try and do is we're going to try and algebraically manipulate this function so what's inside the absolute value bars is the same as what's inside these two absolute value bars. And then we'll do a substitution so that we can relate epsilon and delta. And again, we're only going to do the easy ones of this. So a quick example. So we're going to prove this. So here's my proof. I want to prove that the limit as x goes to -2 of 4x plus 5 is equal to -3. And if you graph it, you can do, this is a linear equation that has a slope of 4 and a y-intercept of 5, so it's pretty steep. So if I go back to -2, get -3 there, it seems reasonable. And so we want to prove this. So we're going to say let epsilon be greater than 0, and we're going to say that the absolute value of 4x minus 5 and then minus that -3, we're going to say the absolute value there is less than our epsilon. Now that is, let's go back a slide, that is me setting up this first partial statement there. All right. And then I'm going to say, and I'm going to say let the absolute value of x minus, well, let's see here, it's going to be -2, is going to be less than delta, whatever that is. Okay. So just real quick, let's simplify this particular side and say that that's absolute value x plus 2 less than delta. No, I think we'll just stay with that. That looks pretty good for right now. All right, so let's start again. So these are my starting statements, and we'll start again with a statement here. So absolute value 4x minus 5, put that in parentheses, minus negative 3 is less than epsilon. And so let's simplify what's inside the parenthesis here. So I'll have minus negative is like plus positive, and I made a mistake here, folks. I have a plus here and I put a minus there, so I want to change that to a plus. I want to change that to a plus. I'm sure you saw that. I'm laughing at Mr. McCulley already. It's too early in the year for that, but we'll get past it. So let's minus negative is like plus positive, so I have 4x, 5 plus 3 is 8, and we're talking less than epsilon. Now again, what was the goal? Let's go back. The goal is to algebraically move the second statement in a way that epsilon and delta are scalars or each other. So we're trying to manipulate what's inside the absolute value to look like this x minus c. So I'm trying to make it look like x plus 2. Well, look what I have here. I got 4x plus 8. That's just off by a scalar, and that's what we're trying to figure out. So I'm going to factor out that 4, and now I have my x plus 2. Still absolute value less than epsilon, and this is absolute value, and absolute value makes everything positive. So what I can do is I can factor out this 4 and put it outside the absolute value, because this would be positive, and then x plus 2 inside the absolute value less than epsilon would also still be positive, so I can do that. That's not going to be a problem. Divide both sides by 4. I've got absolute value x plus 2 less than epsilon over 4. And so now I have my relationship between delta and epsilon. And so I can say for any epsilon greater than 0, let delta be equal to epsilon over 4. And then that limit will be true. So the relationship, delta will be one fourth whatever epsilon is. And then we can guarantee that regardless of how close we get to this limit, this negative 3, we can create a delta that's also that close. That's how we're doing it. All right. I'm sure you have questions. We'll move on. So finding the limit numerically by filling in a table and checking. All right, so here we have this table, and I don't have a graphing calculator emulator at my home computer, so I'm hoping that we can all put in by now an equation into our graphing calculator. So off to the side here, I'm putting in my graphing calculator x minus 3 over the quantity x squared minus 9. And so I'm going to put that in. So parenthesis x minus 3 divided by parenthesis, and I closed the top parenthesis when I was on top, x squared minus 9. And so I'm going to go to my table setup. Since the distances between these independent variable values are different. There's not the same distance in between each one. I'm just going to change my independent variable to ask. I'm going to go to my table, and I'm just going to type in my number. So 2.9. When I type in 2.9, I get 0.1694. When I type in 2.99, I get 0.1669. When I type in 2.999, I get 0.16669. When I type in 3, I get an error. And that makes sense because 3 squared minus 9 is 0. And then 3 minus 3 is 0. 0 divided by 0 is undefined. So if I go 3.001, I get 0.16669, and then 3.01 I get 0.1669, and then 3.1 I get 0.639. 0.1639. I'm not quite sure why those don't match up. Maybe I copied wrong. That seems odd. I don't know why. Anyway, so it looks like we're getting pretty close to 0.6669. And again, I don't like saying that we're going to get, 1/1000th, tens, hundreds of thousands, 1/1000th away, and that gives us a definite value. But this is at least gives us a good idea that it's probably 1.6 repeating, and 1.6 repeating is 1/6, I think. Let's see if I do that. Let's do that real quick. 1 divided by 6 is, 1.6 repeat, or 0.16666 repeating. So we're going to guess this is 0.16 repeating like that, or 1/6. That's our guess. All right. Use the graph to find the function. Graph of the function to find the limit. And so here I'm dusting off piecewise functions, and you're going to see a lot of piecewise functions this year. So it's good that we start these off early. And so let me pull up a Cartesian graph here. Oops, I didn't want to do that. And let's move this down here. Let's move this over here so everybody can see. Okay. You know what? Let's grab that. It's not gonna let me do it. All right, no biggie. X squared plus 3 is a graph that looks like this. But at x equals 1, we get 2. So technically, we end up with a open circle here at 1, and we have the value at x equals 1, we have 2, so that's my graph. So they want us to find the limit as x approaches 1. Now, at x approaches 1, the value is 1. So as we're getting closer to from the left-hand side and closer from the right-hand side, the function tends to point to 4, even though the value of the function is 2 at x equals 1. So even though the value of the function is 2, the value of this limit, the limit as x goes to 1 of f of x, that's going to be 4. And so it's what the function points to more than the actual value. And I cannot stress, that is the #1 takeaway. It's what the function does from the left and the right, not the value of the function at whatever that constancy is. Okay, folks, well, that's all I got. So today's Star Wars fun fact of the day. In 1976, when the original Star Wars came out, they didn't have nice robotics like they did now, so they actually put a guy inside R2-D2. His name was Kenny Baker. He has recently passed, but he shared an anecdotal story that he played R2-D2 so well that when the cast used to break for lunch, they would forget that he was inside and would leave him locked inside, and he'd have to yell and scream to get them to come let him out so that he could go have lunch with everybody else. Well, I hope you have a good day, folks. I will see you in class. Goodbye.